Welcome to our lesson on the algebraic properties of matrices. In this video, we'll explore how matrices behave under various operations like addition, scalar multiplication, and matrix multiplication. Let's begin with matrix addition. For these properties to work, we need matrices of the same size. Let's consider two matrices, A and B, both of size 2 by 2. The first property is commutativity, which means that A plus B equals B plus A. Let's verify this with our examples. Next, we have associativity, which states that A plus B plus C equals a plus B plus C, regardless of how we group the additions. Then we have the additive identity property. There exists a zero matrix, O such that A plus O equals A. Finally, for additive inverse, every matrix A has a negative matrix negative A, such that A plus negative A equals the zero matrix. Next, let's discuss scalar multiplication. This is when we multiply a matrix by a regular number, which we call a scalar. The first property is distributivity over matrix addition. This means that k times the sum of A plus B equals k times A plus k times B. For example, if k equals 2, then 2 times the sum of A plus B equals 2 times A plus 2 times B. We also have distributivity over scalar addition, which means that the sum of scalars k plus L times A equals k times A plus L times A. Next is associativity of scalars, which states that k times L times A equals k times L all times A. Finally, the multiplicative identity property states that 1 times A equals A. Now, let's move on to matrix multiplication, which is more complex than the previous operations. For matrix multiplication to work, the number of columns in the first matrix must equal the number of rows in the second matrix. Let's recall how to multiply two matrices. If we have a 2 by 2 matrix A and another 2 by 2 matrix B, we compute each element of the product by taking the dot product of rows from A with columns from B. The first property of matrix multiplication is associativity. This means that a times B times C equals a times B times C, regardless of how we group the multiplications. Next, we have distributivity over addition, which comes in two forms. A times the sum of B plus C equals a times B plus A times C. And the sum of a plus B times C equals a times C plus B times C. For the multiplicative identity, there exists an identity matrix, I such that a times I equals I times A equals. Note that I is a square matrix with ones on the main diagonal and zeros elsewhere. An important property to remember is that matrix multiplication is generally non-commutative. This means that a times B is not necessarily equal to B times A. Let's verify this with our examples. Now, let's discuss the properties of matrix transposition. Remember that the transpose of a matrix, denoted as a transpose, is obtained by flipping the matrix over its main diagonal, turning rows into columns, and vice versa. The first property is that if we take the transpose of a transpose, we get back the original matrix. That is, A transpose transpose equals A. Next, the transpose of a sum equals the sum of transposes. So, A plus B transpose equals a transpose plus B transpose. For scalar multiplication, k times A transpose equals k times A transpose. Finally, the transpose of a product has a special property. A times B transpose equals B transpose times A transpose, with the order reversed. Let's wrap up with some special notes about matrices. First, any matrix multiplied by the zero matrix gives the zero matrix. That is, a times O equals O times A equals O, as long as the dimensions are compatible. For invertible matrices, there exists an inverse matrix, A inverse, such that a times A inverse equals A inverse times A equals the identity matrix, I. Not all matrices have inverses. For a matrix to be invertible, it must be square, and its determinant must not be zero. If a matrix is invertible, then its inverse is unique. Let's summarize what we've learned about the algebraic properties of matrix operators. For matrix addition, we have commutativity, associativity, additive identity, and additive inverse. For scalar multiplication, we have distributivity over matrix addition, distributivity over scalar addition, associativity of scalars, and multiplicative identity. For matrix multiplication, we have associativity, distributivity over addition, multiplicative identity, and most importantly, non-commutativity. For transposition, we have properties relating to double transposition, sums, scalar multiplication, and products. Understanding these properties is essential for working with matrices in linear algebra, computer graphics, machine learning, and many other fields. Thank you for watching, and I hope this video has helped you understand the algebraic properties of matrices.